95%, that is how much energy your light bulb throws away. You flip the switch, electricity flows in, and for every 100 units of energy you pay for, 95 of them come out as invisible heat. 5 little units become light. That is not an approximation. That is not a rough guess. That is the measured, confirmed, published number. And it has been that way since Thomas Edison screwed in his first working bulb back in 1879. Over 100 years of engineering progress. We split the atom. We flew to the moon. We built machines that can add 1 billion numbers in 1 second. And the light bulb sitting in your kitchen is still an expensive space heater that happens to glow a little. So the obvious question is, what the hell went wrong? Were the engineers asleep? Did nobody try? Because it seems like the kind of problem a clever person could fix in an afternoon. You have got a hot wire in a glass jar. It glows. Most of the glow is the wrong color, invisible, wasted as heat. So just make the wire glow differently, make it put out more of the right color. Redesign the filament, use a better material, coat the glass with something clever. 140 years. And nobody could manage that? That is what most people think, and I want you to sit with that feeling for a minute, because it is a perfectly reasonable thing to believe. The light bulb looks like an engineering problem. It looks like something you could optimize the way you optimize a steam engine or an airplane wing. Tinker with the parts, improve the materials, squeeze out more performance. And in fact, people did try. They tried very hard. Edison himself tested thousands of filament materials. Carbon, bamboo, platinum. Then in the early 1900s, tungsten came along. And that was a genuine improvement because tungsten can get hotter before it melts. Its melting point is around 3,400 degrees Celsius, which is extraordinary for a metal. So you can push a tungsten filament to about 2,700 Kelvin, maybe a bit higher, and get a brighter, whiter light than Edison ever saw. They also tried filling the bulb with different gases. Argon, krypton, nitrogen mixtures. The gas slows down the evaporation of the tungsten so the filament lasts longer and you can run it a little hotter without the filament destroying itself. Then came halogen bulbs. Clever idea. You put a small amount of halogen gas, usually iodine or bromine, inside the envelope. What happens is a chemical cycle. Tungsten atoms evaporate off the hot filament, combine with the halogen gas near the cooler glass wall, then drift back toward the filament, where the extreme heat breaks the compound apart and redeposits the tungsten. It is a recycling system for the filament itself. This means you can push the temperature up another few hundred degrees without the filament thinning out and snapping. Every one of these tricks helped a little. They moved the efficiency from maybe 2% up to around 5%. Some specialty halogen lamps might reach 8 or 9, and then everything stopped. Not because people gave up. Not because the funding dried up. It stopped because the engineers hit a wall. And the wall was not made of metal or glass or money. The wall was made of physics. See, to understand what is really going on inside that bulb, you need to forget about engineering for a moment and think about what it means to be a hot object. Anything that has a temperature above absolute zero radiates energy. Your body does it right now. The walls of this room do it. A cup of coffee does it. Everything that is warm sends out electromagnetic radiation, and the character of that radiation, the mixture of wavelengths, depends almost entirely on one thing, the temperature. This is not a guess. It is one of the most precisely confirmed facts in all of physics. A hot object emits a very specific spectrum of radiation determined by its temperature. The relationship was worked out in the late 1800s, and it is called the blackbody radiation curve. If you heat something to, say, a few hundred degrees, nearly all the radiation comes out as infrared. You cannot see it. You can feel it as warmth on your skin, but your eyes are blind to it. As you raise the temperature, the peak of the radiation shifts to shorter wavelengths. First deep red, then orange, then yellow, then white, then blue. The hotter the object, the shorter the peak wavelength. This is Wien's displacement law, named after Wilhelm Wien, who pinned it down mathematically in 1893. The peak wavelength equals a constant divided by the temperature. Simple and merciless. So consider our tungsten filament. It runs at roughly 2700 Kelvin. You plug that number into Wien's law, and the peak wavelength comes out at about 1070 nanometers. Do you know where visible light lives? Between about 380 and 700 nanometers. The peak of the filament's radiation is way out in the infrared. not slightly outside the visible range. Significantly outside. The whole mountain of radiated energy is centered on a wavelength your eyes cannot detect at all. Visible light is just a skinny little tail on the left side of that mountain. Imagine you are standing at the base of a huge hill. The summit is over there, 1,000 nanometers out, buried deep in invisible infrared territory. You are looking for light in the visible band, which is a narrow strip of ground between 380 and 700 nanometers. You are standing on the slope of this enormous hill, way off to one side, and you are only catching the little trickle of energy that spills into your strip. That is what your eyeball is doing when you look at a light bulb. It is intercepting the crumbs falling off the edge of a feast you cannot see. That is why 95% of the energy is wasted. It is not a design flaw. It is the blackbody spectrum doing exactly what physics demands at that temperature. Now you might say, fine, so heat the filament more, push it to a higher temperature, shift the peak closer to visible wavelengths. And yes, in principle that works. If you could run a filament at, say, 6,000 Kelvin, like the surface of the sun, the peak would land right in the middle of the visible spectrum, and you would get a beautiful white light with much less waste in the infrared. The sun is actually a very efficient visible light source if you think about it, precisely because it is so hot. But tungsten melts at 3,695 Kelvin. You cannot run the filament anywhere close to 6,000 degrees. It would not just melt, it would evaporate explosively, and tungsten already has one of the highest melting points of any element on the periodic table. There is nothing better to switch to. Tantalum melts lower, rhenium melts lower. Carbon can handle extreme temperatures, but carbon filaments in a bulb oxidize and crumble unless you keep them in a perfect vacuum, which creates other problems. Edison started with carbon, remember. We moved to tungsten because it was better. There is nowhere left to go. Even if you could somehow find a magical material that survives 6,000 degrees, you still have problems. At those temperatures, the radiation is so intense that the energy consumption would be colossal. The Stefan Boltzmann law says total radiated power goes as the fourth power of the temperature. Double the temperature and the total energy output jumps by a factor of 16. You would need enormous electrical input just to maintain that temperature. It would be like trying to fill a bathtub with the drain wide open. The hotter you go, the faster energy pours out in every direction. So the constraint is not laziness. The constraint is that the laws of thermal radiation lock you into a spectral distribution based on temperature, and the temperatures you can actually reach with real materials are too low to put the peak where you need it. Let me say that again a different way, because it is worth really feeling this. Every hot object in the universe radiates according to the same curve. It does not matter if it is a filament, a star, a glowing poker, or a blob of molten lava. Temperature sets the spectrum. You do not get to choose which wavelengths come out. Nature has already made that choice for you. You are trying to negotiate with a law of physics, and the law does not negotiate. But there is something even deeper here, and it connects to one of the most important revolutions in the history of science. Back in the late 1800s, physicists were trying to derive the exact shape of this blackbody radiation curve from first principles. They had the experimental data, they knew what the curve looked like. They just needed a theory to explain it. The first attempt used classical physics. Treat the radiation as waves bouncing around inside a hot cavity. Apply the standard rules of thermodynamics and calculate how much energy should come out at each wavelength. Two physicists, Lord Rayleigh and James Jeans, did exactly this, and their formula worked beautifully for long wavelengths, the infrared end. But as you move to shorter wavelengths toward the violet and ultraviolet, their formula predicted that the energy should keep rising, endlessly, without limit. According to classical physics, a hot object should radiate infinite energy at short wavelengths. This was obviously wrong. A hot oven does not blast out deadly ultraviolet rays and fry everyone in the room. But the math said it should. Every step of the calculation was impeccable. The logic was airtight. And the answer was lunacy. The prediction was so absurd that it got a name, the ultraviolet catastrophe. It was not a small error or an off by 10% discrepancy. It was a total, spectacular breakdown of classical physics when applied to radiation. The theory went to infinity, and reality stayed calm and finite. Something fundamental was wrong with the entire picture. The fix came from Max Planck in 1900, and he did not come to it happily. Planck was a conservative physicist. He did not want to overthrow anything. He wanted to make the numbers match, so he tried a mathematical trick. He found that he could get the right curve, matching every experimental measurement perfectly, but only if he assumed that energy is not emitted continuously. Instead, it comes in tiny discrete packets, lumps. He called them quanta. The energy of each quantum is proportional to the frequency of the radiation. High-frequency light, like ultraviolet, requires bigger energy packets. And because bigger packets are harder to produce at a given temperature, the radiation at short wavelengths gets suppressed instead of blowing up to infinity. The curve turns over and drops down, exactly as the experiments demanded. Planck himself thought this was probably just a mathematical convenience. He expected someone would eventually find a proper classical explanation. Nobody ever did, because there is no classical explanation. Energy really does come in lumps. That single idea is the foundation of quantum mechanics. The entire 20th century of physics, from semiconductors to lasers to nuclear energy to the transistor in your radio, all of it flows from that one strange insight. And where did it come from? From trying to understand why a hot object glows the way it does. From trying to understand, in a very real sense, why a light bulb is so wasteful. So when someone tells you the incandescent bulb is inefficient, they are correct. But the reason has nothing to do with bad engineering. But the reason is that glowing hot objects obey the Planck radiation law. And at the temperatures we can achieve with real materials, that law says most of the energy will come out as infrared. Full stop. You can be the greatest engineer who ever lived, and you cannot make a thermal emitter at 2700 Kelvin put most of its energy into visible light. That is like asking water to flow uphill. The physics forbids it. This, by the way, is what makes the light-emitting diode such a fundamentally different kind of invention. An LED does not work by being hot. It works by a completely different physical mechanism. Inside an LED, you have two layers of semiconductor material doped with different impurities. One side has excess electrons. The other side has holes, which are places where an electron is missing. When you apply a voltage, electrons flow across the junction between these two layers. As each electron crosses and recombines with a hole, it drops from a higher energy state to a lower one, and the difference in energy gets released as a single photon. The wavelength of that photon, and therefore its color, is determined by the energy gap of the semiconductor. Gallium nitride gives you blue, indium gallium nitride gives you green, aluminum gallium indium phosphide gives you red. There is no blackbody spectrum. There is no mountain of infrared waste. You are not heating something and hoping the right wavelengths trickle out. You are directly converting electrical energy into photons of the color you want. That is why an LED can be 10 or 15 times more efficient than an incandescent bulb. It is not a better version of the same idea. It is a completely different idea. And that distinction matters enormously. In science and in life, there are two kinds of problems. There are problems where you need to push harder, be smarter, optimize better within the existing framework. And there are problems where the existing framework is the problem, where no amount of cleverness within the old approach will ever get you past the wall. You need a new approach entirely. The light bulb sat at 5% efficiency for a century, not because nobody tried, but because trying harder within the framework of thermal radiation cannot work. The blackbody curve has no loopholes. It took a completely different physical mechanism, electrons jumping between energy levels in a semiconductor, to break through the wall. And ironically, the physics that explains why the old bulb fails, Planck's quantum theory, is exactly the physics that makes the new solution possible. Quantum mechanics explains the disease and provides the cure. There was one beautiful attempt to split the difference, and I want to mention it because it is so clever. Researchers figured out that you could surround the filament with a special structure, a kind of photonic crystal, that reflects infrared radiation back onto the filament while letting visible light pass through. The filament reabsorbs the waste heat, which means you need less electricity to keep it at the same temperature. In principle, this could push incandescent efficiency past 40%. In the laboratory, they reached about 6 or 7%. Still far from the theoretical maximum, but the concept is gorgeous. You are not fighting the blackbody curve. You are recycling the parts of it you do not want. But think about how roundabout that is. The filament radiates exactly the spectrum that physics demands. Then you build an elaborate, nanostructured mirror to catch the 95% you do not need and feed it back. Compare that to an LED, which just makes the light you asked for in the first place. One approach accepts the law and tries to work around it. The other approach sidesteps the law entirely. So here is what I want you to take away from all this. The next time you flip a light switch, remember that the old bulb, the one your grandparents used, was never badly designed. It was perfectly designed. It did exactly what physics says a hot object should do. The problem was never in the bulb. The problem was in our question. We were asking a heated wire to do something that the laws of nature do not allow. And it took a revolution, the invention of quantum mechanics itself, to understand why that little glowing wire in a glass jar sits at the crossroads of thermodynamics, electromagnetic theory, and quantum physics. It is one of the most deeply constrained devices ever built, not constrained by human imagination or a lack of trying, constrained by the structure of reality itself. The blackbody curve is not a suggestion. It is a verdict, and no amount of tungsten, no amount of halogen gas, no amount of ingenious filament geometry will ever overturn it. Sometimes the most important thing a problem can teach you is that you are asking the wrong question. And the light bulb for 140 years was physics telling us exactly that. If that does not make you look at a light bulb differently, I do not know what will. Tell me this. What other everyday object do you think has a hidden physics wall that we have been banging our heads against for years?